Welcome to the Planet of Maths channel. In this episode, we will talk about operations on roots. We will solve such examples in this video. But to move on to the harder examples, let's start with something like this. We have the square root of 4 plus the square root of 16. A number like 4 and 16 are numbers that can actually be square rooted. The square root of 4 is 2, and the square root of 16 is 4. We add it up and we get 6. In example B, we have a somewhat similar situation, but we have numbers at the front. However, this doesn't change much for us. We know the square root of 25. The square root of 25 is 5. The square root of 9 can also be calculated, and it is equal to 3. Here between this number 3 and this root, there is multiplication. So here we have 3 times 5 plus. And here between the 2 and the root, there's also multiplication. So we have 2 times 3. We can multiply 3 by 5 to get 15. Here 2 by 3 is 6. And after adding, we get 21. End of example B. But what to do if we have an example C where we have the square root of 2 plus the square root of 8? The square root of 2 and the square root of 8 cannot be calculated. So sometimes we can help ourselves with the fact that some of these roots can be partially simplified, meaning factoring out. This is the square root of 8. We take this number 8, and we will factorize it into prime factors. For this, knowledge of prime numbers will be needed. Prime numbers are those that have only 2 divisors, and those are numbers like 2, 3, 5, 7, 11, 13, 17, and so on. Each of these numbers has only 2 divisors, and we'll use these numbers one by one, checking as we go. Checking if 8 can be divided by 2, and it can. So I write down the 2 and divide. 8 divided by 2 gives me the result of 4. This 4, once again I check if it can be divided by 2, and it actually can be. 4 divided by 2 gives me the result of 2, and this 2 again divided by 2 gives us the result 1. When I get 1 here, that's the end of this factorization. Now I do something like this. If I have a square root, and I have, then I'm looking for pairs here. These two 2's make a pair, and from that pair, I get one new 2. So here I have a 2, and if I want to write down the square root of 8, so that new 2 goes before the root. And under the root, I write what is left apart from these pairs. I have one pair of 2's here, but apart from that, I have one 2 left that doesn't have a pair. And that's exactly what I put under the root. That means the square root of 8 is the same as 2 square roots of 2. So I'll rewrite this square root of 2, and instead of the square root of 8, I'll write 2 square roots of 2. Now I can add this, because it's the square root of 2, so 1 square root of 2 plus 2 square roots of 2, together that makes 3 square roots of 2. And this is the result for example C. In example D, I have 2 such roots, so I proceed similarly. The numbers under the roots cannot be simplified at this moment. That's why I will be factoring. First, the number 54. I'm checking if 54 divides by 2, and it does divide by 2. So 54 divided by 2 is 27. 27 cannot be divided by 2, so I take the next prime number, which is 3, and 27 can indeed be divided by 3. And from this, I get 9. I'll still be able to divide the 9 by 3, so I write 3 and divide. 9 divided by 3 gives me 3. And the 3 can be divided by 3 again, resulting in 1. At this point, I have the end of the prime factorization, and I can write what the square root of 54 is equal to. In the front, I pair up. Here I have 2 3's. From those 2 3's, I'm getting a new 3. And this 3 goes here in front of the square root. Under the square root, I'm writing what I couldn't pair up. 2 and 3 don't pair up because they are not the same numbers. So I multiply these 2 numbers together. 2 times 3 gives me 6, and I write it here under the root. So, instead of the square root of 54, I can write that it is 3 square roots of 6. I'll do the same with the number 24. I'll factor the number 24 into prime factors. It definitely is divisible by 2. 24 divided by 2 is 12. 12 divided by 2 is 6. 6 divided once more by 2 gives 3, and 3 can only be divided by 3, resulting in 1. Now I pair up. This 2 pairs with that 2, and a new 2 is formed. I'll put this 2 in front of the root. That means the square root of 24 factorized has the 2 at the beginning, and under the root, I'll write what I couldn't pair up, which is this 2 and this 3. I have to multiply them. 2 times 3 is 6. From this, I have 2 square roots of 6, and I put it instead of this square root of 24. 3 square roots of 6 minus 2 square roots of 6 equals 1 square root of 6. We simply write it as the square root of 6. Example E. Here again we have numbers under the roots that cannot be square rooted, so we break them down into prime factors. First number 98. 98 is divisible by 2. 98 divided by 2 is 49. Then 49 can't be divided by 2 anymore. The next prime number is 3, but 49 is not divisible by 3 nor by 5. 49 can only be divided by 7. 49 divided by 7 gives me 7, and 7 is only divisible by 7. I get 1, and that's the end of this factorization, which means that I can write down a simplification of this root. I have a pair of 7s here, and from these 7s, I get a new 7. This 7 goes here at the beginning. Under the square root, I put what I couldn't pair up, which is this 2. The square root of 98 is precisely that. Now I'll factor the number 50 into its prime factors. The 50 is divisible by 2. I get 25 out of this. And 25 won't be divisible by 2 or 3. It will only be divisible by 5. 25 divided by 5 is 5, and 5 divided by 5 gives me 1. End of prime factorization. Now I'm reading. The square root of 50 is equal to, and here I have a pair of 5s, so I get a new 5 from these two 5s. I'll put this new 5 here at the beginning. Now I'm left with this unmatched 2. I put this 2 under the root here. Then my calculation will be like this. I notice that there is multiplication between the 2 and the root, just like here. I rewrite the 2, and instead of this square root of 98, I'll use 7 square roots of 2. I'll add this 3 multiplied by, instead of the square root of 50, I'll take what I calculated, which is 5 square roots of 2. Now I multiply 2 and 7, which gives 14 square roots of 2. 3 will be multiplied by 5, resulting in 15 square roots of 2. This square root of 2 does not get multiplied with anything. Finally, I add 14 square roots of 2 plus 15 of the same square roots of 2. That makes 29 square roots of 2. Another similar 1 example. I have the square root of 27, which I can't calculate. The square root of 75 can't be calculated either. So I factorize. First, the number 27. Here I recall prime numbers again. 27 is not divisible by 2. It is only divisible by 3. So I write 3 here. 27 divided by 3 is 9. 9 is still divisible by 3 to get 3. And 3 divided by 3 gives a result of 1. So the square root of 27 is equal to, from these two 3's, one new 3 is formed, and I place this 3 here at the beginning. And under the root, I put what could not be paired, that is this one and only 3. I have the square root of 27, and I still have to do the square root of 75. I obviously need to factor the number 75 into its prime factors. 75 is not divisible by 2, but it is divisible by 3. 75 divided by 3 gives me a result of 25. These 25 is not divisible by 3, but by the next 5, it is already divisible. 25 divided by 5 is 5, and 5 divided by 5 is 1. End of factorization, I'm looking for pairs. This 5 and this 5 make a pair, and from these two 5s, I get one new 5. I put this new 5 here at the beginning. Under the root, I put what I have left. I have this 3 without a pair, so I put it under the root. Then I get 4. We already know that here we have multiplication, and instead of the square root of 27, I give 3 square roots of 3. Then it's subtract 3, and instead of the square root of 75, I put 5 square roots of 3, and here is multiplication. I can then multiply 4 and 3, which gives me 12 square roots of 3. And here, 3 multiplied by 5 gives me 15 square roots of 3. The square roots here had nothing to multiply with, and I subtract 12 square roots of 3, subtract 15 square roots of 3, so here I end up in the negative. The result will be negative 12 minus 15, which is negative 3 square roots of 3. This is the result for this example. In the example H, there is a fraction bar, and I have 3 roots that do not match at all right now, but I will factor them into prime factors, and maybe something will come out of it. First, we take number 12. The smallest prime number is 2, and 12 divided by 2 gives me 6. 6 divided by 2 is 3, and 3 divided by 3 gives me 1. From these two 2's, a new 2 is formed, and I give this 2 here at the beginning, and under the square root, I give a 3. That is what has left without a pair. The next number is 48. 48 divided by 2 gives me 24. 24 divided by 2 is 12. 12 divided by 2 gives me 6. 6 divided again by 2 is 3. And 3 only divides by 3, which gives 1. Here, my factorization ends. And I read what the square root of 48 is equal to. I pair up. Here, two 2's can be combined into a new 2. And from those two 2's, I get another new 2. I multiply these two 2's that come from these pairs. 2 times 2 is 4. Under the root, only the number 3 remains here, which means it is the square root of 48. And there is also the number 27. 27 is not divisible by 2, but it divides by 3. 27 divided by 3 is 9. 9 divided by 3 is 3. And 3 divided by 3 gives us the result of 1. Thus, the square root of 27. Here we pair up, and from two 3's comes a new 3. It goes to the front here. And under the root, I put what couldn't be paired, which is the 3. Then here on the fraction line, I will have 2 multiplied, and instead of the square root of 12, I give 2 square roots of 3. Then I add 5 multiplied, and instead of the square root of 48, I give 4 square roots of 3. At the bottom, 4 is multiplied by, and instead of the square root of 27, I put 3 square roots of 3. We're getting closer to the end. 2 times 2 gives 4, so I have 4 square roots of 3, plus 5 times 4 gives me 20 square roots of 3. And at the bottom, 4 times 3 gives me 12 roots of 3. At the top, I add 4 square roots of 3 and 20 square roots of 3, which makes 24 square roots of 3 in total. And at the bottom, for now, no changes, 12 square roots of 3. Because here it is an invisible multiplication, I can cancel out the square root from the top and the square root from the bottom. The square root of 3 and the square root of 3 cancel each other out. There's only this much left, 24 over 12. 24 divided by 12 is simply 2. And this is the result for this example H. And finally, 2 more examples with cube roots. We have the cube root of 16, which we cannot calculate, and we have the cube root of 54, which we also cannot calculate. But we factor them into prime factors and see what happens. The first number is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. And 2 divided by 2 is 1, which means the cube root of 16. And because we have a cubic root, so we don't group in pairs, but in 3's. Yeah, we have 3 identical 2's here. From these 3 2's, we make one new 2, and place this new 2 here at the beginning, before the root. And we place this single 2 under the radical. Now the number 54. 54 divided by 2 gives 27. 27 cannot be divided by 2 anymore, but it can be divided by 3. 27 divided by 3 is 9. 9 divided by 3 is 3. 3 divided by 3 is 1. This is my factorization. I am writing down the cube root of 54. Here I have 3 3's. Thus, I combine them into a new number 3, and this new 3 I place here before the root. And under the cube root goes what is single, which is this 2. I have these roots now. I can return here. The square root of 16 is basically 2 cube roots of 2. And this cube root of 54 is 3 cube roots of 2. So now I have identical roots. Here are 2 of such roots plus 3 of the same roots. From this, I get 5 cube roots of 2. Example I is finished. And example J, similarly, cubic roots of numbers that we cannot find the cubic root of, 40 cannot be rooted. So I factor it into prime factors. 40 is divisible by 2. That makes 20. 20 is also divisible by 2, so that makes 10. 10 divided by 2 is 5, and 5 is only divisible by 5, resulting in 1. End of factorization. I'll write it down. The cube root of 40 is equal to, I'm looking for triples, and I have 3 2's here. Out of these 3 2's, a new 2 is created, and I put this 2 here in front. And under the cube root, I write what I have left, which is 5. I have sorted out this root. Now the number 135 remains. 135 is not divisible by 2, but it is divisible by 3, because when we add the digits 1 plus 3 and 5, it equals 9. The sum of the digits is 9, and such a number is divisible by 3 if the sum of the digits is divisible by 3. And we have to divide it somehow. Out of this, we have 45. 45 can still be divided by 3, resulting in 15. 15 is divisible again by 3. From this, I get 5, and this 5 is only divisible by 5. And that means the cube root of 135 is equal to... Now, I'm looking for triples, and I have 3 identical 3's, which give me one new 3, which I place in front of the root, and under the cube root, I write what is left, which is this single 5. If there was anything more left here than just this 5, you would have to multiply them together. Here's only a 5 left, so I write it here and go back to the example. 4 at the beginning. Invisible multiplication becomes visible. Instead of the cube root of 40, I write 2 cube roots of 5. Plus 2 multiplied by what I got here from this root, which is 3 cube roots of 5. I multiply what is outside the root, 4 times 2, which makes 8 cube roots of 5. Here outside the root is 2 and 3. Multiplying these gives 6 cube roots of 5. And now I can add them because I have identical roots, so they add up. 8 plus 6 gives me 14 cube roots of 5. And that's all for this video. Thank you for watching, and I invite you to tune in for the next episodes on the Planet of Maths channel.